This is the intuition video for question 1A of the 2009 MAT paper. In this question, we're given IA, which is an integral of x squared minus a squared from 0 to 1, and considered as a function of a, and we're asked to deduce what is the minimum value of I of a as a varies over the real numbers. So first things first, a good idea is most likely to plot the curve that's actually being integrated. So we'll plot y equals x squared minus a squared. The shape of this graph isn't too surprising. We have a quartic here, so i.e. the highest power of x is to the 4, and having 3 turning points in this case makes sense. If you have got an n degree equation, you can have at most n minus 1 turning points, which is the number we have here. So let's highlight the area we actually care about. So this corresponds to IA. Let's vary a and see what happens. So if we tend a towards positive infinity or increase it, I of a increases as the graph, all the points between 0 and 1 on the graph move vertically upwards as a increases. And similarly, as a tends towards minus infinity, I of a tends to infinity. But somewhere here we must have a minimum of our function, I of a. So let's have a look at the graph of I of a and see what we get and see if it makes sense when compared to this. This is our graph of I of a against a, and first thing to note is the function's always positive, which makes complete sense. If we get the original graph back up, we see for all values of a the curve's always gradient above the x-axis, and so the integral over any region of this curve will also give a positive value, so our blue curve is always above the x-axis. Now we were asked to find the minimum value of this curve, so algebraically we can work out it's attained here, since we can rearrange I of a into this form up here, and from here it's clear. And also looking at this form and the graph, it's clear that we actually have a line of symmetry in the line x equals a third. And at this point here, we have our minimum, and it is 4/45.